So blood transfusions are super, super important in healthcare. But moving forward, we may actually be relying on bacteria as a way of making blood transfusions more efficient. We're going to talk all about this and so much more on today's episode of Short Stories of Bacteria. Hey everybody, welcome back to another episode of Short Stories of Bacteria. I, as always, am your host, Dr. K, and I'm here to guide you through yet another episode chronicling the lives of the tiny and infamous, that would be, of course, the incredible, amazing, and fascinating bacteria. Today, guys, I have a really cool story today. Talking about the relationship between, oddly, bacteria and blood transfusions. Not really something that you would expect there to be a connection between, but there actually is a really cool connection, especially in this emerging healthcare and emerging biotechnology. We're going to talk all about that in like 5 seconds, but first what I would like for you to do is hit that like, share, subscribe button on YouTube. If you're following us on Spotify or on Apple Podcasts, don't forget to hit that follow button so you can stay up to date with all of the good stuff that's coming out of the Short Stories of Bacteria empire as the empire continues to build. But that's enough of that. Let's move on to the actual science. So let's give a little bit of background here. You may be aware of this, that blood transfusions are super, super important. For whatever reason, whether it be someone's, got a really, really bad cut and started bleeding all over the place, or if someone has an infection or something like this, for whatever reason, sometimes people need new blood, right? They need new blood. And this is where blood transfusions show up. So blood transfusions are actually older than I initially thought they would be. It turns out the earliest blood transfusions showed up in the 1500s, which is wild to me. But ever since then, ever since those 1500s, then people have been focusing it and getting it better and getting it healthier, a little more hygienic. But the overall goal of the blood transfusion, of course, is for someone to receive blood, right? To receive blood intravenously. You take some other blood and then you put it into your body as a way of replenishing when you lose blood for whatever reason. So it's really, really important. Doctors use it all the time. And this is why oftentimes you'll see these blood drives, right, where people go and they donate blood so that people in hospitals, if they're short on blood, they have something that they can use to fill up the tank, for lack of a better phrase. So yeah, doctors use blood transfusions all the time. They're super important as a way of keeping people alive. Now, that's all well and good. But you may have heard of this notion that there's these things called universal donors or universal acceptors. And so what is that all about? In order to understand that, we need to understand this basic premise that you can't just take anyone's old blood and give it to anyone else, right, for a blood transfusion. Only specific people can pair with other specific people when blood transfusions are occurring. Now, why is that? If you zoom in on the blood of an individual, you really look at them. If you look at their cell membranes, because if you've ever seen a red blood cell, it's like a little donut-shaped thing. But if you zoom in right on the membranes of those blood cells, you're going to see a whole bunch of different types of proteins, sugars, lipids, all these different things. Now, in particular, there's a series of sugars that are different from types of red blood cell to types of red blood cell, right? So let's take a group of red blood cells. Let's call them group A, right? They'll have a series of sugars on their membrane. So we'll call them, a type A blood cell, right? Then let's take another one. Let's call it type B, and that also has a series of different kinds of sugars, right? Different sugars on type A, different sugars on type B, right? There's also a third type, which we'll talk a little bit more about in a second, called type O. Those also have something a little bit different, but we'll focus on it later. But for now, what I want you to think about is there's different types of red blood cells, type A and type B, and there are different sugars associated with each of those. The second point is that I guess then there's a third as well, which is type AB. So there's type A, type B, and then there's a mix of those two, type AB, right? So these different types of red blood cells have different sugars associated with their membranes. In addition to these different sugars, the red blood cells can have different proteins associated with their membranes as well. And there's in particular one called an RH factor. You may have heard of this before. An RH factor is, it's an inherited protein that sticks to the exterior of red blood cells, right? And so there's a further way that we can divide these red blood cells. So there's type A, right? That has a certain type of sugar on the membrane. And there's type A positive, which has a certain type of sugar on the membrane and this RH factor protein. Or you can have type A negative, which has those sugars on the exterior, but it doesn't have that protein, right? Similarly, you can have type B, has a set of B associated sugars, what I'll call them. And then on the exterior, it has the Rh factor again, so it'd be type B positive, or you can have type B negative, so sugars on the outside, but no Rh factor. And then finally, you can have type AB, which has a mix of these sugars. AB positive has the Rh factor, AB negative doesn't have the Rh factor. So why does this all matter? Why does it actually play a role? Why can't I just take one person's blood and then put it into another person's blood, even if they have all these differences in terms of their membranes? And the reason why has to do with the immune system, right? So our immune system interfaces with red blood cells all the time, right? So we have our white blood cells, which are busy saving us from bacteria and viruses and all these different things, and they interface with red blood cells. Now, the white blood cells that we have in our body are very familiar with the red blood cells that we have, and specifically the proteins and the sugars that are on the membranes of these cells, of these red blood cells. Okay? So if you were going to take, and remember, we're dealing with a large amount of blood cells. If you were going to take a new set of red blood cells that has a different sugar content or different protein content, then our immune system will look at that and be like, oh my gosh, I don't know if that's me or if that's some kind of invasive thing, right? And because of that, if it can't really tell whether or not it's friend or foe, it's just going to err on the side of this is foe and then try and destroy everything. So number one, the transfusion won't take because all the red blood cells are going to be attacked by the immune system. And number two, there's going to be these localized areas of inflammation and where the immune system is trying to destroy everything in that particular area, right? So you need to have something that the immune system is going to be like, okay, I recognize you as a red blood cell, and specifically I recognize you as my type of red blood cell, and then they'll take them into the fold, and then the transfusion can actually be helpful. Okay, so that's why it matters what type of blood goes from the person who is getting the blood extracted from them, and then the person who's getting the actual blood transfusion. Okay. Now, this brings up something called a type of blood called O blood. Now, O blood is different from type A or type B or type AB for a couple different reasons. So, O blood doesn't have those sugars on the exterior. It has some sugars, but don't worry about that. It doesn't have those sugars on the exterior, right? So, it can't really trigger the immune system like type A or type B or type AB will. Okay, so but we do have like a different. Okay, we'll hold that. So it has it doesn't have these sugars on the membrane. The second point is type O can also be divided into type O positive and type O negative. So it can have the protein on the exterior, or it cannot. So it can be type O positive where it has that Rh factor, or it can be type O negative where it doesn't have that Rh factor. Okay? Now type O negative has a pretty, for lack of a better phrase, has a pretty naked membrane. It doesn't have any sugars, it doesn't have any proteins, and so the immune system, when it runs into type O negative blood, it's like, oh, it's just a red blood cell, because I recognize the red blood cell, and it doesn't have all this other gunk on it that could distract me from recognizing the fact that it's a red blood cell. Okay? So type O negative, because it doesn't have all this stuff on the exterior, because it doesn't have these sugars and doesn't have these proteins, that serves as what's called a universal donor. Pretty much any immune system can look at that and be like, oh, wow, it's a red blood cell, so we're totally fine, right? And this is why people who have type O negative blood, typically, people will reach out to them and be like, hey, have you considered donating blood? Have you considered donating blood? Could you please donate blood? The reason being that they are universal donors, that their blood can be taken in by pretty much anybody, and the immune system won't freak out. Okay, so that's a second really, really important point. Type O negative blood doesn't trigger the immune system, and as such, type O negative blood is the universal donor. Now, if you were an industrious scientist, you'd be like, well, gee, it would be really, really cool if we could take that type A blood and that type B blood and maybe the type AB blood. If we could figure out a way of clipping off those sugars, clipping off these proteins, right? Maybe we could just make more universal blood, and then we wouldn't have to worry about shortages of type O negative blood, right? There's a finite amount of people. I think I saw a stat that something like 7% of people are have type O negative blood, And so there's a finite amount of blood. You could have these blood shortages. And so what a scientist could be like, hey, what if we could figure out a way to cut all those proteins and all those sugars off of type A, B, and AB, and then that would make it look like type O negative blood. That's an emerging hypothesis. That's something that people... Now, it turns out that people have been working on this for a lot longer than I would initially thought. The initial studies to work on this, I think, showed up in the 80s. But it's actually really, really tough. The reason why is that not that it's hard to find something that will chop sugar and protein off of a membrane, but you need to have something that's very, very specific. So it's only going to cut off a certain type of sugar and only cut off a certain type of protein. And you also have to have something called enzyme efficiency. So it has to be able to do it rapidly, and it has to do that. Yeah, so it has to be able to do it rapidly and really well, right? Now, that's kind of hard to do. You had to find very, very specific proteins to be able to do that sort of thing. But there were a couple of people at the Technical University of Denmark, a series of bioengineers, so score one for the engineers, I guess. And what they were doing is they were approaching it from the perspective of bacteria. Okay. Now, bacteria are really, really good at chopping up sugars and chopping up proteins, sometimes for seemingly unknown reasons, but bacteria are super diverse, so they do a whole bunch of whacked out things. But the point being is we have a whole bunch of different bacteria out there that can cut a whole bunch of different sugars and proteins. And so what this group of bioengineers was doing is like, okay, what if it'd be really cool if we could find a bacteria that would specifically shear off those sugars and proteins as a way of producing more O negative blood. That was the game plan moving forward. So that's what they did. So they found a bacteria called, this is a doozy of one, guys, Akkermansia mucinifera. Let me try it again, Akkermansia mucinifera. So that's a great bacteria name, I guess. And so what they did with this Akkermansia mucinifera is they identified this new protein that was able to not only was it really efficient at this, but it was able to cut off sugars off of type A, type AB, and type B red blood cells, right? It was cutting off those sugars as a way of, and they were using that as a way of trying to make it look more like O negative blood. Now, what's really, really wild then is if you took these new, what I'll call edited A, B, and type AB blood cells, if you took those and then you put them in contact with an immune system, so blood plasma, right, with a kind of a separated immune system, it brought down the immune reaction. In the case of specifically type B, it brought down the immune reaction by 90%. By 90%. That's utterly wild. That's a ridiculous dampening of the immune system and the immune reaction, right? So now we have this really cool mechanism by which we took an enzyme extracted from bacteria, used that to shear off sugars off of, say, type B blood, and then that new type B blood then didn't cause a strong immune reaction. Utterly wild stuff, totally wild. Now, moving forward, there's still a lot of questions. There's obviously the Rh factor, which we talked about. It doesn't solve all of these problems that we have, that we're still working on with blood transfusions, but it's really huge, the fact that we have an enzyme now that can cut off sugar and in such a way that the edited red blood cell doesn't stimulate as strong of an immune reaction, at least in a test tube. So let's wrap this up and get out of here. Point number one, blood transfusions are super, super important. Doctors use them all the time as a way of replenishing blood in people who are obviously lacking in blood. Point number two, because type O negative blood doesn't trigger the immune system because it doesn't have those sugars or those proteins on the membrane, it's known as a universal donor. Point number three, it'd be really, really cool for us to use bacteria or the enzymes extracted from bacteria as a way of shearing off sugars and shearing off proteins as a way of producing more type O negative blood. And then finally, point number four, using a bacteria enzyme in Akkermansia mucinifera, a couple of guys were able to chop the sugar off of A and B cells as a way and produced a form of blood, at least in the case of type B, we're able to produce a form of blood that caused a much more dampened immune reaction. So really, really cool story. I'll keep you guys informed, see if anything else comes out of that story. But it's a really neat instance of how not only bacteria live in and around us and all over us, but we can actually use bacteria as a way of helping the medical field in something as intimate and cool as a blood transfusion. So that's enough for today. Thank you guys ever so much for tuning in and listening to another episode. And I will see you guys again next week on another episode of Short Stories of Bacteria.
Hey everyone, thanks for watching that video. If you guys enjoyed it, if you liked what you saw, don't forget to hit that like, share, subscribe button, and I will hopefully see you guys in the next video. Later!